It's just going to be a quick review on enthalpy. So thermochemistry stuff that we did earlier this year. So you're going to start using that again as we move into thermodynamics again here, and just energy changes and heat changes within a chemical reaction. So remember, enthalpy is just the change in energy in a chemical reaction. So if delta H, that's your enthalpy, remember, your change in heat. If delta H is positive, that means there's an increase in energy. So that means that your reactants start off low, increase, your products would be higher energy. Okay, there's an increase in that. If delta H is negative, that means it's exothermic. Okay, there would be a lowering of energy from reactants to products. So endo, exo, remember, if we're adding heat for a reaction to happen, that's endo. If heat is coming out, that is exo. Delta HF, the heat of formation of a compound. Okay, heat of formation of a compound would be that table we've looked at before. So, for example, the heat of formation of C3H8 is that. What that means is if we take carbon plus hydrogen, which is diatomic, and make that compound. Now, if we balanced it, we always want to keep that as a 1 right there. So this would have to be a 4, and this would be a 3. Remember, there sometimes will be fractions in these, but the overall enthalpy change for this reaction is negative 103.8 kilojoules per mole. So that is the heat of formation. So that means making this compound from its elements. So if I took carbon plus hydrogen and made that compound from its elements, that would be the heat of formation. Hang on a second. Sorry, it's going to be a little wobbly for a second. Turn a little caffeine on there. So this would be an exothermic reaction making C3H8 from its elements. Okay, so that is the delta H for this reaction, which is the heat of formation for that compound. Remember, individual elements have no heat of formation. So the diatomics and elements without charges have no heat of formation. Ions do. Carbon dioxide's heat of formation, water's heat of formation. So remember, if we know the heat of formation for each of those compounds, we can do products, the sum of the products minus the sum of the reactants. So remember, this is per mole of carbon dioxide, so I got to do 3 times a negative 393.5 plus 4 times a negative 241.8. Okay, that's the change in enthalpy of the products minus a negative 103.8 plus 0, because that's a 0, so don't worry about that. Okay, so that'll give you the overall delta H for that reaction. So that ends up being, the delta H ends up being negative 2044 kilojoules. So that is the delta H for that reaction. So it's an exothermic reaction. In other words, these are lower energy, these are higher energy. As this reaction happens, you're giving off this many kilojoules of heat per mole of this compound. You're giving off this many kilojoules of heat per 5 moles of oxygen they're used. You're giving off this much heat per 3 moles of carbon dioxide. Okay, so this is the amount of heat given off per those moles. So if we did a stoichiometry question, if I said, okay, we have 30 grams of carbon dioxide that were made in the reaction, I want to know how much heat was released. If 30 grams of carbon dioxide was made, how much heat was released? So we're going to say, at carbon dioxide is 44 grams per mole. And then just say that for every 3 moles of CO2, there's that much heat released. For every 3 moles of CO2, there's negative 393. I'm sorry, not that. That's the heat of formation part. There's negative 2044 kilojoules of heat released. So in this reaction, if 3 moles of that were made, that much heat is released. So if 30 grams of carbon dioxide was made, you would have a negative 1394 kilojoules of heat that was released to the surroundings. So that means heat is being given off to the surroundings. It's exothermic. I put some problems on Schoology to do. It's not very many of them, but it's from chapter 8, a little bit older stuff.